In this session, once again, I would like to demonstrate a combustion problem, and probably we will be addressing another new issue of communicating our results of simulation which are not part of the report generation used in Aspen. So we have a fuel composed of methane and ethane, equimolar composition, is burned with excess air, and we wanted to obtain a flue gas on a dry basis with 9% CO2. So in order to get this requirement, we may have to adjust the airflow rate that gives us the required composition of CO2 in the flue gas on a dry basis. So simulate this process and try to find out what is the excess air, completes RSAT analysis, and the moles of flue gas including water vapor per mole of fuel burned. So how are we going to report these answers? Now you might have done such problems while solving maybe your mass and energy balances. Now let us see how to handle this problem using Aspen. So we have two components involved in the fuel, methane and ethane, and then air is going to be used as the other combustion. So air is being considered as a mixture of oxygen and nitrogen, and the combustion. So these are all the components we are trying to involve. Once again, we may be interested in mass balance and calculate the percent excess air. So the property model may not really make much of a difference. So I can choose even ideal property model. So go to next, go to simulation environment, and then create the flow sheet. So here, composite of methane and ethane is mixed with air, and this is converted in a reactor. Converted in a stoichiometric reactor, complete combustion can be assumed. And what would be the combustion products we'll be able to get? Because 100% fuel is combusted, we are having excess oxygen, excess all the nitrogen that is inputted, along with the products formed, carbon dioxide and water vapor. But we wanted to get the composition of the flue gas on a dry basis. So how will you be able to get the composition on a dry basis? So I'm trying to use a component separator by which I'll be removing water. So whatever gases that are coming out here will be representing the composition of the flue gas on a dry basis. So let us make the connections, stream connections. So you have fuel, air, and the combined fuel is entering into the reactor. Then it is sent into the component separator. Now we have the unconverted gases accepting accepting water vapor. So this is all what we have. So let us go and provide the problem definition. So what we are required to identify with respect to S1, or probably I can rename them for convenience. This is the fuel, and this is air. Similarly, I will write this as dry flue gas, dry, and this is water. Let's go to the next input. So it is asking for air. So as I said, temperature and pressure may not really matter. So the composition of air we know, which is normally used for combustion calculations, 0.21, theoretical calculations, 0.79. But how much air we need to supply, we don't know. Anyway, we need to adjust this flow rate. So let me start with something like 3000 kilomoles per hour. This is a wild guess. Of course, you can calculate what is the theoretical requirement depending on the amount of fuel and utilize this. So having defined air, let us go to the next input step. This is with respect to fuel. Again, temperature and pressure may not matter. So let me assume the flow rate of, because we are interested in calculating excess air, so it doesn't matter. So I am assuming the flow rate of fuel at 100 kilomoles per hour, having the composition of 50% methane and 50% ethane. We have defined both the input streams. Now go to the next. Okay, mixer, nothing is required. Now this is with respect to the reactor. So let us also assume it is entering at 25 and 1 bar. Now the reactions. There are two reactions now. We have methane, stoichiometric coefficient 1, reacting with oxygen 2, and giving rise to carbon dioxide 1 mole, 1, and then water 2. And we assume that 100% conversion of methane is going to take place. Next. So similarly, I can define another reaction. So this is ethane, coefficient is 1, plus oxygen. We can find out C2H6. So 2 moles of carbon dioxide are going to form for every mole of ethane, and for water, so C2H6, so 3 moles. So what is the oxygen requirement? For every mole of ethane, we require 2 moles of oxygen and 1.5 moles of for water. So total 3.5. Then once again, I am assuming a complete conversion of ethane, because only we are supplying air in excess. So having defined this reactor model and reactions, go to the next. So this is with respect to, so you can define with respect to water. What is the purpose of our component separator? We wanted to separate all the water that is coming out, that is coming into this separator, completely into this stream. But none of the other components must be allowed. So you are removing water, and all these components, whatever are present, will go into the other stream, that is the dry stream. So we have given the required input, so we should be in a position to run the problem. Yeah. So let us go and see the results. For example, let me see whether whatever we have assumed with respect to air flow rate, whether it is enough for us to completely convert methane and ethane. So you can see all the methane and ethane is completely converted. Of course, we have given a lot of air, because roughly only 50% is consumed. 630 out of that 355 is still coming out. So we may have to anyway adjust this based on the composition. Now let me see the composition of the dry flue gas. So we have got the composition of carbon dioxide is 0.05 or 5.2% based on the assumed flow rate of A, right? So, but we need to get this at 9% on a dry basis. See that there is no water, there is no methane and ethane because they are completely converted. So you are left with only oxygen, nitrogen and carbon dioxide. So you are able to see the composition of the flue gas on a dry basis. Now we need to adjust the flow rate of air such that this composition becomes 9%. So in order to do this, once again, let us go back and use a design spec. New. So what is the target variable, measured variable? Mole fraction of carbon dioxide. So let me name it. It's a stream variable. It is going to represent the mole fraction of one component. Stream is dry flue gas. Component is carbon dioxide. Right? So what is the spec? What is the value that we are interested in? Mole fraction of carbon dioxide. This is how I named it. this should be equal to 0.09. And so how are we going to achieve this? By varying the air flow rate. We started with an initial assumption for the air flow rate at some 3000 or so. So let us take this as stream variable. Stream is air, variable is mole flow. Remember what is the value that we have started with? We started with 3000 kilomoles per hour. Gave us some 655. So the excess air was too high. So probably we may have to reduce this air flow rate. Anyway, let me start with 1000 to maybe 3000. I expect the solution to lie somewhere in between. So with this, we can see what is going to happen to this design spec. So we are using some air flow rate, calculate the composition of CO2 in the dry flue gas, compare it with the requirement. If the requirement is not met, we are going to adjust the air flow rate till the requirement is met. So you can run this problem now. Again, we are using secant method. By carrying out about 6 iterations, we were able to come to a convergent solution. Once again, you can see the measured variable is here, the manipulated variable is here, and all the 3 blocks are going to be iterated till you reach a convergent solution. Whatever blocks that are involved between the measured variable and manipulated variable forms an iterative loop in the case of specification. So when we started with 3000, we got a mole fraction of about 5.2%, which we have already seen. But when the flow rate becomes about 1792, the composition of the flue gas will be around 9%. So this is the air flow rate. Now the question here is, having solved this problem, we wanted to calculate the percent excess air, complete RSAT analysis of the flue gas. We already have this RSAT analysis of the flue gas. RSAT analysis is nothing but the composition on a dry basis. So we already know the composition which can be obtained from Aspen reports. So this is the composition of the dry flue gas or RSAT analysis of the flue gas. So one part is directly available. The moles of flue gas including water vapor per mole of fuel burned. So we started with 100 moles per hour and we will be able to note down what is the number of moles of flue gas including water vapor. So if you want to look at that value, so this will involve all the flue gases including water vapor. So if you know this moles, divide that by the number of moles of fuel that you are using, which is equal to 100. So we should be in a position to report this. But remember, this is not actually part of the report made by Aspen. So you are generating about 1917 kilomoles per hour for every 100 kilomoles per hour of fuel burn. So what is the ratio? This is about 19.17. Anyway, you will be able to have all the information required in order to calculate. What about the next problem? How are we going to calculate the percent excess air? You know the percent excess air is equal to the actual amount of air used minus the theoretical air required divided by the theoretical air. So we need to calculate the theoretical air. So we have 50 kilomoles per hour of methane, so which requires 100 moles of oxygen. Similarly, 50 kilomoles of ethane require 3.5 times, that is 175 kilomoles per hour of oxygen. So total we have 275 kilomoles per hour divided by 0.21 will give you the required oxygen, the required air, theoretical air. You will be able to note down what is the actual air supplied. We already have this value. So the actual air supplied is 1792, but the theoretical air required is something like 375 divided by 0.21. So we will be able to calculate the percent excess air. But how are we going to represent these values in your simulator, right? How are you going to obtain these results and report them? So there are 2-3 ways. You can use either Excel or maybe a Fortran code to write some of these values which are not part of your Aspen report. For example, I can do, we will be spending some time later to talk about some more applications using this calculator, but let me show you one such way of communicating some of the results that we want. So what is that we want? The variable is, we wanted to know the yield input flow rate of yield. So this is going to be a stream variable. Again, stream variable, and this is air flow rate. Variable is mole flow. So from this, we are going to obtain the flow rate of input A, which I would like to import from Aspen, right? Then what is that we are trying to do? Once we know the A input flow rate, I already know the theoretical A required, so I should be in a position to calculate the percent excess A. So this is the only one variable that I am using. So next, some of you who are experienced with Fortran probably will be able to understand this. So you need to write the executable statements starting from the 7th column, right? So let me make some calculations first. So percent excess A. Okay. Excess can be written as, we know what is the actual A that is coming in, which we have obtained this information from Aspen. And I know what is the theoretical oxygen required. So this is 375 divided by 0.21. Of course, you can calculate and put that value, divided by 375 divided by 0.21. Whatever is the actual amount of excess A used. We need to multiply this with 100 in order to get percent excess. Okay. Let me put this 100 also, so that we'll be able to get this in terms of percent. So in order to do this, what is that we have done? We are importing the value of yield that is inputted into the simulator and calculated the theoretical yield, and using these two values, we are calculating the percent excess yield. Now in order to communicate this value, I am going to use, right? I may not be spending much time in explaining this, but you can, those of you who are experienced with Fortran, you should be able to understand this. So let me write this as 10. So this is what I have done. So go to next. So you can see, because of the calculator block, we were calculating the percent excess yield and reporting that value as 38%. Right? It's coming as 0.38, even though you are putting it as 100. Let me check up that. So this is how, in fact, you should be in a position to communicate some of the results which are not part of your Aspen reports and write all such values into a file, and you should be in a position to even print that file as it is. So this is the total flow of air in kilomoles per hour. Sorry, it is not 375, it is only 275. 50 kilomoles of ethane required 3.5 times 175. 50 kilomoles of methane required 100. 100 plus 175 is 275. That is the mistake we did. That's why the percentage is coming very low. So let me set and run this problem again. The percent excess yield is about 36.88%. So in the same way, if you want, you should also be able to report the ratio of moles of flue gas divided by mole of fuel burned by reading the values of flue gas generated, moles of flue gas. We already have the information about moles of fuel, so you should be in a position to report that. Probably we will see some more applications of using calculator block separately. In the same way, we should also be able to do this in a calculator block using Excel instead of Fortran. So let me also show you. Probably I'll try to show you this in another example. So with this, I would like to